Hi everyone, I hope you are all doing well and welcome to Autodesk PowerMill. So today we are going to start the module number 3, which is all about the 3D toolpaths and machining strategies. So in this module, we only discuss about the 3D toolpaths. In the previous module, we just discussed about the 2D curves and 2D toolpaths. So this time we have a 3D model, and on a 3D model, we are going to apply 3D machining strategies. And you see, all these strategies which we have here are the model area clearance, model rest area clearance, model profile, model rest profile, slice area clearance, and slice profile. So all these 6 tool path machining or strategies are for roughing operation, not for the finishing operation. So you get all these 6 tool paths and machining strategies apply on model to create a rough sketch of the object on or using a PowerMill software. So let's get started and do the first toolpath strategy, which is named as model area clearance. So let's get started. So I have here PowerMill. So we are going to load a model in this software. Okay, so loading a model or import a model is very easy. Here you can go to models here, right click and select on import model option, or you can go to the file and import, and you will see that we have certain options here, model and examples. So I'll go with the examples first because we'll perform the all toolpath strategies by using all these example models here. So I'm using the calling.dgk file. You see over here that this named as calling.dgk file. So DGK stands for Delcam Geometry. As you know that this software was firstly named as Delcam and Delcam PowerShape for designing software, but now it's owned by the Autodesk company. So this file is known as calling.dgk. So this is a 3D surface model and is being prepared in a PowerShape software, which was previously known as Delcam PowerShape. So I'm going to open this software, and you see that this model is open in this software, and you see that this model is a surface model. It's not a solid model, it's a surface model. So definitely it is being made on using a software name as PowerShape software. Okay, so we have loaded a model inside this PowerMill. Now what we have to do is we have to create some certain setups and settings. What you see over here is a work plane, and this work plane was generated during the preparation of this model. Okay, so this model during this preparation of this model, this work plane was selected, and by default it is selected as this. So we have one work plane, active work plane, and this is the model work plane. Okay, so right now we have to create a block for this object. What is the purpose of block is to define the area of model which it covers, so we can define the block to the machines that this model will be taken by this block or this raw material. So how we can get the block? You will see the options on a home, and in a home tab you will get the block option here. So just click on the block, and here you see that we have to define the block by using the box option, picture, triangle, cylinders, and cylinder sector, spun pattern sector. So this is a 3D model, and this model contains length, width, and height. So we need a box. So I have selected a box. So the coordinate system is active work plane. The active work plane, which I have just discussed, that this model is prepared on a certain work plane, and this is the work plane which is active, and this work plane is defined as a work coordinate system for this workpiece. So that's why we have an active work plane here. So now it's time to define the limits of the block. So we have minimum, maximum, and length. So by clicking on the calculate button, you will see that the computer automatically calculates the X, Y, and Z direction for this model and create that the length of this model is 210 millimeters, approximately 210 millimeters, and in Y direction, or we can say that the width is approximately 100 millimeters, and the depth or the height of the model is 55 millimeters. Now, the one thing you should have to know about the minimum and maximum. So you know that the coordinate system has maximum value and the minimum values. So Z direction from this point to on the above side will be represent as Z positive, and from this point to downward side it is represented in negative direction. So what we have here is represented the maximum value in positive and the minimum value in the negative direction. Same as if we talk about the material on the positive side. So from this active work plane, from this point to up to right side in X direction, we have positive material up to 150 millimeters approximately, and in the negative direction we have approximately minus 60 millimeter material. So in the Y direction, definitely we have the material in Y positive direction is 50 approximately, and in Y negative direction we have in approximately 50 millimeters. So this is defined by the active work plane. So just click on OK and accept it. Now what we have to do is we have by default active work plane. So we have to create a work plane for this model. So this also defined as the work coordinate system. So by defining the work coordinate system, you have to define the work plane. So how we can define a work plane? I say that I have to select the work plane on the top of this block. So how we can select it? We have certain options here. You can go to the work plane over here, or you can access the work plane by the manager area or explorer area. So right click on this and you'll see the different options. Just create a work plane here, or get work plane from the model, or create and orientate work plane using different options. We have work plane at point, multiple work plane from the 3-point and 3-point arc, aligned with the geometry and revolve, and work plane using the work plane position using the block. So if I'm going to select this option, we have different options over here, but if you are going to apply this option, this gives you multiple options to define the work plane. You see that I've selected the work plane using the block positions, and there are certain positions here. The green ones on the top side shows the top side, the golden one in the middle, and in red one at the bottom of the workpiece. So we have three positions on this side, at the center 3 positions, and 3 on the corner edges. So same as here we have. So by default we select the center of the block at the top position. Okay, so this position will be the Z work plane or work coordinate system. So right now this work plane is, you see over here that it's light in color, but we have to define, or we have to activate this work plane. So go to work plane again and right click and click on the activate work plane to active this work plane. So if you active this work plane, the work plane will get active, and you'll see that the block is changed right now. The block direction is changed. Why it's changed? Because the block was created by using this work plane, which was the default work plane of the model. Now the work plane has been changed because you have active and create a new work plane. So what we have to do is just go back to the home tab and just click on the block, and now we have an active work plane which is named as 1. So we have to calculate the work plane block according to the active work plane. So click on the active and it will automatically active that thing. So you see that it just converted all the measurements and get it half. So what you have here is 210 in total length, and it just converted or divide the 210 millimeters approximately into positive and negative direction halfway. Okay, so as it should be on the y direction, and the z direction is in a negative because all the materials goes back to downward direction. So this is what we have the work plane setup. You can also right click here and rename it. So I'll say that it's a work plane W1. This is a work plane number 1. So now it's time to apply the model area clearance. So as you know that this strategy is applied on a 3D model or a 3D surface. So that's why we call this model area clearance. And in this model area clearance, we are going to apply the roughing operations, all the roughing operations to give a certain shape to the block. So in such type of operations, you will get a rough idea how your workpiece is just looks like. And for this operation, what you need is you just need a tool. You can apply the patterns, you can apply the boundaries on this side using the model area clearance. So let's do the toolpath. So on a home tab, you will see the toolpath tabs over here, or you can either create by using right click on the explore area, create a toolpath, or you can also get the access from the tabs and text commands here, and you will see the toolpath. So I'm going to click on here, and by clicking on this side, you will see the 3D area clearance toolpath. And in the 3D area clearance toolpath, you will see that model area clearance strategy over here. So just click on this and click OK. Now the model area clearance toolpath strategy, the tool parameters are being shown here. So first thing, by giving you an idea how it looks like, so just give the name of the toolpath for just the sake of reference and to know what we are going to do actually. So I just give this model area clearance. Okay, so right now the model area clearance, we have the name here. Now go to the different parameters and check. So as you know that we have already created a work plane, so it is just named as W1. So we don't need to create another work plane. Block, yes, we have already set up the block, so we just don't need to change the block settings. Tools, oh, we don't have a tool. So for the roughing operation, you need a tool. So for roughing operation, as you know that you can apply the flat end mills to create roughing operations, because we have to remove a lot of materials from the surface. As you see that we have a block here and we have to perform roughing operation, and a lot of material have to be removed from that block. So for that purpose, you need to select the tool. So we have certain tool options over here. So we have flat end mill, we have bar nose, bull nose, or we can also say that tip radius tool, and then some tapered spherical tool, and some taper tip tools, disc tools, center tip tools, radius tapping tools, bar nose tools, grooving tools, turning tools, and probe. So just click on the profile named as end mill tool. Give name that, for example, I'm going to use a 10 millimeter flat end mill for this operation. So I'll write at 10 and flat, F for flat, E for end, and M for mill. So 10 millimeter flat end mill, or if you want to give millimeters, you can write it millimeter. So this defines that it's a 10 millimeter flat end mill tool. I'm using it. So the diameter of the tool is 10 millimeters, and the length, you have to get the length according to the tool using in the market. So for 10 millimeter tool, you have a length of 75 millimeter by default, and the number of tool number is 1, and the number of flute is 4 fluted tool. Okay, So now it's time to get to the other option, which is the machine tool. We don't need to change any settings here. And the limits, we have to define the boundary. I will discuss this later about the boundary option in a rest material option. Okay. So in the upcoming video, we will discuss about the limit option. So now just go to the other option, which is model area clearance. So we have to define the model area clearance style. So how it just looks like and how it cut down the material. So this is says just offset all. We have 4 options here: raster, the other option is offset model, and the offset all vertex. So we have 4 options here. The first one is the raster. This defines that the cutting tool will perform its operation at an angle. So it will just do all the operations at an angle. Either it should be 90 degrees, 0 degree, 180 degree, and 45 degrees. So only the cutting tool path will be created in an angled form, in a straight way, in a linear way. But if we talk about the offset model, then it will just follow the model and create an offset of the model to create a tool path according to the model geometry. So what you see over here, if we go to top position, we say that this is the profile of the model. So it will take a pattern of this profile, and around that profile it will create a tool path at an offset, and the offset model will be discussed on the step over distance. We say that this step over is 5 millimeters. So this outer boundary of the model will be created, and the tool path will create according to 5 millimeter offset to this model. So this is what we call the offset model. And offset all means that all over the operations we are going to perform, this should be according to offset all. So first of all, we discussed the raster, offset model, offset all. Let's say that vertex. In a vertex type, the computer will definitely calculate, or the software will calculate according to its own way of cutting. It's a vertex style, it's an irregular style. It's not followed by the offset or raster. It's just a irregular pathway to cut down that material. So this tool path is mostly used when we have to cut a lot of material from the surface, and we have to create long depths of cuts and shorter step overs. Okay, so we can use the offset model, which is most appropriate with this type of model which we have here, which we have loaded here. So now the next thing is cut direction of profile. So we have 2 profiles, either should be in the conventional way, or either it should be the climb way, or in any way that it will be cut from the left to right or right to left, or will define any way. Okay, so the area of cutting, so the profile cutting should be the climb way, and the area of cutting, or we can say that the roughing operation should be done in any way. So the next thing is the tolerance. It defines the tolerance in the tool path tolerance and cutting weight tolerance. So it's 0.1 millimeters. So let's define it 0.001 millimeters. Okay. The next thing is the thickness. If you want to say that we want to remain some material on the surface, so you can say that we have to define the thickness of the cutting operation, that it will remain 1 millimeter distance at the bottom and 1 millimeter distance on the sideway. Let's say that this one represents that the tool path will create the tool path, and it will remain material from the floor side 0. So if I say that it's 1 millimeter, then this will say will not remove 1 millimeter material from the floor side. And on this option, it will remain or will not remove any material from the wall up to 1 millimeter distance. Or we can say that 1 millimeter distance will be not removed from the wall side. Or you can just click on here to get it all the way from 1 millimeter floor side and 1 millimeter from the wall. So why we do this? We do this for the roughing operation, because we are going to perform the roughing operations, and 1 millimeter material is safe for the finishing operation, so that the roughing tool will cut down this material and make the size accurate to the model which we have loaded here. Okay, so say that we have to remain some material on the stock, so it's 0.05 millimeter. The next thing is a very crucial step, which is the step over distance. We have to define how much amount of percentage the cutting tool will cut down the material from the side way or in an axial way. So as you see that it shows as 5 millimeters, this means that our 50 millimeter of cutting tool will cut down the material and 50 millimeter of the tool will be on the side way. So only 50% of cutting tool will be utilized. The next thing is the step down. We have to define the step down or depth of cut. At each step, the cutting tool will be down and cut down the material. So it's 5 millimeter. This means that the cutting tool will down and plunge into workpiece, taking 5 millimeter step and cut down that material. So you have to define the step of depth and step over according to your cutting tool material, workpiece material, and machine capacities and cutting feed and speeds. So if you have a light weight material or less hard material, as we can say that aluminum, brass, silver, copper, so you can take high step over and high step downs. But if you have a hard material to cut down, so for that you need to take light step over and light step downs. So let's go to the other option, which is the offset model, offsets. So we'll state that maintain the cut direction and remove the cusp, and we have defined the cut directions all the way. Just go back to the other option which we have is the rapid moves. So we don't need to change anything over here. So because these are not relevant to this model, but we can define all these things which are right now not appropriate at this time to discuss. It's time to just discuss about the model area clearance. So just discuss the rapid moves. As you know that the cutting tool cut down the material and just go back to its height. So where it should have to take the rapid moves, so you have to define the safe area. So we are using the plane, type is plane, and the work plane is the W1 which we have already selected. So you have to calculate that. So we have the rapid clearance at 10 millimeters. This means that the cutting tool will take from this point up to 10 millimeters in upward direction, and the plunge clearance will be from this point to 5 millimeter ahead. So just calculate it. You will see that it just go back to this point. Now it's time to apply the lead and links here. So lead and links actually defines the cutting tool to be linked with each other, either how the cutting tool will be enter into the workpiece, how it will just go outside, the first lead, the last lead, and the lead extensions, and the links between the tool paths. So let's go and define the first choice. We have the scheme. I'll say that it's going to be straight down. Just the second one will be straight, and the default will be the safe or scheme way. So also you have to enable the gauge check. This means that it will check the gauges of between the tool and the workpiece stock and the model, all these things. So we have to define these feed and speeds over here. So I have to set the spindle speed of 6000 RPM and the cutting feed rate of 1500 millimeters, and the plunge feed is for 150. Let's make it to 300 millimeters per minute, and the skim feed is by default as 3000 millimeters. It depends upon the feed rate of your machine. So you have to define all these things by calculating the specifications of your machine. So I'm using the aluminum material, so I will definitely use the cutting oil or coolant for my operation. So I'll just select it as flood. So now it's time to calculate the model area clearance. Just click on calculate. So it's going to prepare the block, all these parameters and all these settings to be made to be cut down that roughing operation. So this is how we can set the parameters for the model area clearance. So this will take some time to calculate it. So make sure that you have to wait until this operation will be performed or the calculation will be complete. So it's just taking a lot of time because it depends upon the processing speed of your computer and the RAM and the graphic properties and the processing capability. Okay, so if you have a low specs computer, then definitely it will take a lot of time to calculate. So during the calculation, you don't need to click anywhere on the screen, because if you click, it will be hard on your cutting tool operations calculations. So make sure that you just need patience and step back and see how it just calculating your tool path. So now it's calculating the area clearance tool path. So it just shows the warning that the plunge moves into stock exists at the start of some toolpath segments. An option to select the correction or connection containing these moves can be found within the toolpath edit menu. Okay. So what you see over here, that it just is we have selected the offset model and just created a tool path according to the offset of the model and create a very fine smooth tool path. And you see that we have selected the 5mm depth, so it just created a 5mm depth of the cutting tool. So this is how we can make the model area clearance tool path. So let's go and check the simulation, how it actually looks like. So I just go to simulation and just select the entity which we have. So we have entity of tool path is model area clearance. We have a tool which is 10mm end mill, and we have to set the view mill option to check in a solid way. So I have clicked it here and on the settings, and now just click on the play button to play this simulation. So you see that this is taking a 5mm of depth to cut down that material in an offset way, in an offset model option. So this is how the model area clearance work. So let's say I'm going to increase the speed to speed up the operations. So you see that it just follow the model and taking offset to cut down that material. So just increase the speed. So you see that this is how the offset model area clearance works. So hopefully you understand all the steps which I have defined here by performing the model area clearance toolpath. So that's it for the model area clearance. And thank you very much.